So starting off with the equilibrium constants, we derived equilibrium constants for different reactions. We said that, can we turn that off? Yeah, sorry. So we derived those equilibrium constants for different reactions. We know that K goes as the activities of the products to the powers of their coefficients divided by the activities of the reactants. For acids and bases, they look like what follows: the activity of hydronium ion times the activity of the conjugate base of the parent acid divided by the activity of water times the activity of the acid. For the Ka, for the Kb value, you've got activity of the protonated base times the activity of the hydroxide ion divided by the activity of water times the activity of the base. And then for Kw, we got hydronium ion activity times hydroxide ion activity divided by water activity squared. Now, we're going to talk in just a second about the conditions under which we're allowed to use concentrations, but essentially what we're going to decide is that we can only substitute concentrations for activities when we have very dilute solutions. And the reasoning for that goes back to some of the material we covered last week. But in the case that you have a very dilute solution, your solvent, which is water, is essentially pure. It's almost pure. And we know that the activities of pure substances go to 1, right? Pure liquids, the activities go to 1. So in all of these K equations, we can take that activity of the water and just set it equal to 1, because we've got such a dilute solution that the substance is almost pure. Okay? And so in the case that we have a dilute solution, we're going to say that we can substitute all of these activities with their concentrations. And I just want to remind you real quick about why this only works for dilute solutions. So several weeks ago, we derived the chemical potentials of solutes and solvents, and what we found was that the chemical potential of the solute went as some chemical potential naught plus RT times the natural log of the Henry's law constant times the mole fraction. Now, the solvent chemical potential went just as the mole fraction. You didn't need that Henry's law constant. For the solute, you needed the Henry's law constant. And what we said that was about is that when you've got a solution, it's got some solute in it, the average forces felt by the solute are going to be different than they are in the pure substance. So in the pure substance, you've got solute molecules surrounded by solute molecules, and there's some inherent amount of force that they're being held together with, and so there'll be some resultant vapor pressure that's a function of that force. And you'll have the vapor pressure of the pure substance that's largely a function of solute molecules being surrounded by solute molecules. But in a dilute solution of these solute molecules, the average solute molecule is surrounded by solvent molecules. And so the magnitude of the forces holding that species into solution will be different. They might be greater, they might be less. But what we said is that what we'll do is, instead of saying it goes as the mole fraction times the pressure of the pure substance, that we'll just throw in this constant, this Henry's law constant, that corrects for the observed behavior of the solute in that solution. So the forces might be less than in the pure solute, in which case the vapor pressure would be higher, and the Henry's law constant would be something that was higher than P of the pure. Or the forces might be stronger, and they might be holding that solute into the solution, in which case the vapor pressure would be something lower, and so the Henry's law constant KH would have to be lower than the pressure of the pure substance. But what I want you to note is that this assumes that derivation for the chemical potential of the solute assumes that we've got a dilute solution and that there's some constant average amount of force that molecule is being held into solution with, and that force can be kind of expressed mathematically by throwing in some constant called Henry's law constant, the KH. And the KH just corrects for that force. But now I want you to think back to what we discussed, I think it was a couple weeks ago when we started talking about ions in solution. And we said that when ions go into solution, that what happens is, I'll draw the graph if you remember. What happens is that the activity, not the activity, but the chemical potential lowers as concentration builds. So we had a graph that we showed of chemical potential versus conc ion. And that chemical potential dropped as concentration built, and then it started to gain again as concentration got higher. And we said that the reason that it dropped was a couple of things. First of all, ions attract each other in solution. You got positive charges and negative charges, and as you begin to build up a concentration that's high enough that those point dipoles essentially can feel each other and can exert forces, there'll be some kind of an electrostatic minimization. And so it'll lower the potential just because you're an ion surrounded by other ions that you're attracted to. We also said that there's the shielding effects. And we went through that big derivation where we looked at the force law, the 1 over 4 pi naught, or 4 pi epsilon naught r squared force law. And we said that as we had increased ionic strength, that the shielding between charges became greater, and so the energy requisite to build a charge in that media became less. And so the chemical potential, which you can think of as the absolute energy of the ion in that state, dropped. So as concentration builds, that chemical potential of the ion lowers. Then we have the effect whereas the solution becomes too saturated with ions, it becomes harder and harder to continually add new ions to the solution. And so the chemical potential starts to raise as concentration builds. In short, it's not a safe assumption that you can monitor the chemical potential of the solute by having some constant multiplied by the mole fraction, because the chemical potential does not go as a constant. It's some changing, there's some changing magnitude, or it doesn't go as a constant times the concentration. There's some changing magnitude with concentration. So this is not a good mathematical approximation for the chemical potential of a solution as concentration increases. It does work for very dilute solutions, and it turns out that the mole fraction for dilute solutions is proportional to the concentration of the species. And so we can take this term, RT natural log of KH times XB, and kind of move the KH over there, take XB, and then break the XB part into a constant times concentration, and end up giving ourselves a chemical potential expressed as the concentration of the ion. So that's essentially what we're dealing with when we say that we can express those activities as concentrations. We're dealing with the approximation that we have a very dilute solution and those ions are not interacting, and so in that limit they obey Henry's law. In general, ions do not obey Henry's law, and so this behavior or that model doesn't work. Okay? So really quickly through this. pKs are proportional to delta G. So natural log of K is equal to delta G, negative delta G naught over RT. And you know the pK is the negative of the log of K. And so since log and natural log are proportional to each other, it's a factor of 2.303 in front of those guys. That means that pKa is proportional to delta G of the reaction. So the larger the delta G of the reaction, the larger the pKa. If we have a large equilibrium constant, this is going to mean that we have a small pK. Again, to get K, we have to raise 10 to the negative power of the pK. So the larger the pK is, the smaller the K is. And so the smaller the pK is, the larger the K is. So large K goes to small pK, and small k goes to large pK, right? We've got this relationship. If you take Ka and Kb for a given acid and you write those out, Ka is conc H3O times A conc A minus over HA. Kb is conc HA times conc OH minus over A minus. You multiply those two by each other, and you notice that the HAs cancel out and the A minuses cancel out, and so Ka times Kb ends up being conc H3O plus times conc OH minus, which we know is the K of water. And the K value for water, the dissociation constant for water at 25 degrees Celsius, is 1 times 10 to the negative 14. So that gives rise, if you take the log of both sides, log Kw is equal to log Ka times Kb. So that means that pKa plus pKb is pKw is equal to 14. And so if we have a pKa for an acid, or we have a pKb for an acid, or for a pKb for a base, sorry, we can obtain pKa, or we can obtain the other pK by simply subtracting the value we have from 14. This should all be reviewed from acid-base chemistry. The fact that pKa plus pKb is equal to a constant basically means that as the activity of one species goes up, the activity of another species goes down. Since activities are being expressed as concentrations in the limit of the dilute solution, that means that as the concentration of one species goes up, the concentration of the other species goes down. This makes sense. If you've got a bunch of H plus in solution, you're not going to have a whole lot of OH minus. That excess H plus is going to protonate a large fraction of any OH minus that you have in solution. Okay. So, first two examples deal with determining the pH of a weak acid. Before we do that, we'll talk about the pH of a strong acid. Weak acids don't dissociate completely, and so we have to use the Ka value to figure out how much of that stuff is in solution. Strong acids dissociate completely, and so you can say that conc H plus in the solution is equal to conc HA initial, because all of that stuff is going to end up dissociating, and so pH for a strong acid is equal to negative log of conc HA initial. And the reverse thing will be obeyed by a strong base. A strong base will completely dissociate in solution, and so your POH will be equal to negative log of the concentration of whatever that base was that you stuck in solution. The weak acids obey, they kind of distribute or display different behavior. So example number one, we've got a weak acid at high concentration. It matters that it's at high concentration because at high concentration we're allowed to make the approximation that the equilibrium concentration of HA is about equal to whatever its initial concentration was. So for these problems, we set up an ice table. Your book doesn't show you ice tables. Did you guys, were they introduced as ice tables to you? This is all familiar? Are you raising your hand?
I mean, when you said lines, yes.
Okay, good. All right, so this is nothing new, so we know ice tables. So you express initial change in equilibrium, and so your acid will have some initial concentration. We call that HA. Express concentration of H3O plus A minus. Our change is negative X for HA. It's plus X for H3O plus and A minus. And we end up with this expression that says that Ka is going to be equal to concentration of X squared over 0.15 minus X. Ka for this acetic acid is 1.8 times 10 to the negative 5. Now, because our initial concentration was 0.15 molar, that's kind of a higher concentration, we're going to assume that it'll be safe to take this 0.15 minus X and just set it equal to 0.15, right? That gives us a very tidy piece of math there. Determine X, which is conc H plus. We just take the square root of 0.15 times Ka, and that gives us X is equal to 1.6 times 10 to the negative 3. This is equal to conc H plus. And so our pH will be the negative log of that. Negative log of 1.6 times 10 to the negative 3 is 2.8. We've got about a 2.8 pH for this solution. Now, anytime we use that approximation, we want to check and make sure that it ends up being valid. And so what we'll do is we'll take the value that we get for X using the approximation, we'll compare it to the initial concentration of the acid. You look at 1.6 times 10 to the negative 3, and it's much, much less than 0.15, and so we're going to assume that that it was safe to make that approximation. I think the rule is 5% rule. So if this number is anything greater than 5% of this number, you're supposed to assume that it wasn't safe to make the approximation. You got to go back and do the calculation the other way. But if it's less than 5%, then we assume that our approximation was justified. Problem number 2, same exact acid, but now we're going to say that we're going to start off with a much smaller concentration. We got a 1.5 times 10 to the negative 4 molar concentration of this acid. We set the problem up the same way. We get the same exact equation. 1.8 times 10 to the negative 5 is equal to x squared over conc initial minus x, but this time conc initial is much less. And looking at the relative magnitudes of the initial concentration and Ka, they're kind of close to each other. So we're already assuming that we can't make that substitution. So in that case, we've got to go to the full quadratic formula. We write the expression out in quadratic form. We end up with 1x squared plus 1.8 times 10 to the negative 5x is equal to Ka times conc initial is equal to 0, or minus Ka times conc initial is equal to 0. That's A, B, C form, where A is 1, B is 1.8 times 10 to the negative 5, and C is Ka times initial concentration. Plug in the quadratic formula. You end up figuring out that there are 2 roots. You're always going to take the positive root because the negative root does not fit parameters of our calculation. You can't have a negative concentration. And so we end up with, determining that we've got a concentration of 4.4 times 10 to the negative 5. You can take the negative log of that and it'll give you the pH of the solution. I guess I meant to do that, but I was writing my notes fast and I didn't finish the problem. You'll notice though that the value that we get for X for the concentration, 4.4 times 10 to the negative 5, is not 5% or less of 1.5 times 10 to the negative 4, right? Those are off by about a factor of 10, so that's going to be much closer. So it wasn't safe to make that approximation that conc initial minus X is equal to conc initial. So it's a good thing we use that quadratic form. All right, so we've got another problem in there where we start off with a base. We're looking at a base going into solution, a weak base. They give us the pKa of the base. They say that the pKa is 4.88. We know that if we're looking at a dissociation of a base in solution, that we're going to be needing to use the pKb. So we say that pKb plus pKa is 14, therefore pKb is 14 minus 4.88. We end up with a 9.12 for the pKb. Take 10 to the negative 9.12, that gives us 7.6 times 10 to the negative 10. This is a very small number. Because we have such a small pKb, since we have such a small Kb, we're going to assume that X ends up being very small, and that in this case we can make the approximation that our initial concentration minus X is equal to our initial concentration. Our initial concentration was 0.01 molar, and that small Kb again justifies our approximation. Set up your ice tables. This time we don't have to use the quadratic form. We get that X is 0.01 times, or the square root of 0.01 times 7.6 times 10 to the negative 10. That gives us our OH minus concentration. Take the POH of that, it's negative log of the OH minus concentration, gives us a 5.5. Go back to the relationship pH plus POH is equal to 14. And we've got that pH is equal to 14 minus 5.55 is equal to 8.45. Am I going too fast? I got a lot of material to cover, and I'm assuming this is all review, so I'm just burning through it. If I'm going too fast, let me know, slow me down, but if you guys are cool with this, don't stop. So we're okay up to here? Okay. Okay, so now we've got polyprotic acids. What do we do when we have a species that has more than one ionizable proton? We're going to start off by writing the Kas for both species. We've got Ka1 is H conc H plus times Ha minus over H2A. Ka2 is conc H plus times conc A2 minus over Ha minus. And we're going to note that Ka1 is always going to be a lot bigger than Ka2. And this kind of is what we expect from a basic electrostatic analysis of the problem. You get rid of that first proton, now you've got a negatively charged species. And as you try to remove that second proton from the negatively charged species, the magnitude of the force binding that positive charge to the negative charge is larger. Right? F goes as Q1 times Q2 over 4 pi epsilon naught. And so there's going to be larger forces tethering that second proton to the molecule. And so we can always expect that there's going to be a much lower dissociation for the second proton than for the first proton, so Ka2 much smaller than Ka1. So the problem asks us to estimate the concentration of CO3 2- in the solution. To do this, we're going to start off by rewriting out our Ka2, because Ka2 is the one that has the concentration of CO3 2-. Again, it goes as conc H plus, conc CO3 2- over HCO3-. And what we want to do is we want to look at, well, first we just kind of recast this expression in terms of conc CO3 2-. We get that conc CO3 2- is Ka2 times conc HCO3- over conc H3O plus. And we're going to go back now to the first dissociation to obtain a relationship between conc HCO3- and conc H3O plus. So you rewrite out Ka1. You see that Ka1 has both the activity of H3O plus and activity of HCO3- in them, or in the expression. Remember that Ka1 is much larger than Ka2. And so because it's much larger than Ka2, we're going to run the assumption that approximately these two concentrations end up being equal to each other. So we know that in reality, the concentration of H3O plus is governed by Ka1 and Ka2. And we know that the concentration of concentration of HCO3- is governed by Ka1 and Ka2. Those are both subjected to reactions that change their concentrations. But in this case, because we know that Ka1 is so much larger than Ka2, we're just going to run the assumption that these two concentrations are equal. What that does is it allows us to go back to our expression for conc CO3 2-. We've got the ratio of the two concentrations that we said were about the same because they're governed by Ka1. And so we can just draw a line through these guys and say that conc CO3 2- is equal to Ka2. For that, the Ka2 was, or pKa was 10.25, and so you take 10 to the negative 10.25, and that gives you a value for Ka 5.6 times 10 to the negative 9. Does that problem make sense? Any questions on that one? That one's a little weird. It's a little strange that you end up with a concentration that's actually independent of the initial concentrations of the acid that you put into solution. Again, that all comes from the assumption that the concentrations in this term of HCO3 minus and H3O plus are determined by that first dissociation constant. Because the first dissociation constant is so much larger, concentrations are equal. I'm moving pretty fast, huh? I'm going to run out of things to talk about. All right, so this is a really cool derivation. I definitely I don't know that I'm going to give. I'll probably give you a couple acid-base homework problems. I might give an exam question that's acid-based, but it'll probably be tailored to discussion of activities. I'm really not going to focus on this material in exams or homework. But that said, I really suggest that you go over this derivation in your book. It was really fun. It was really kind of insightful, and at the end, it helps you draw out a nice little curve that relates concentrations of species to pHs. So I meant to say diprotic acid. I wrote triprotic. Sorry, that should be diprotic. So we've got a diprotic acid, and we're going to write out its two Kas. They look as we expect them to. We've got an expression for the total concentration of the acid as prepared. So this is before anything dissociates. How much acid did we put into the mixture? And that total is going to be equal to the equilibrium concentrations of H2A plus the equilibrium concentration of HA minus plus the equilibrium concentration of A2 minus. And so what we're going to want to do is obtain expressions for all of those concentrations. We can start with Ka1 to write out the equilibrium concentration of HA minus in terms of the equilibrium concentration of H2A. We get the HA minus concentration is Ka1 times conc H2A over conc H3O plus. Run back to Ka2 to obtain an expression for conc A minus in terms of conc HA. And you end up with this expression, conc A2 minus is equal to Ka2 times conc HA over conc H3O plus. But we already derived an expression for conc HA, and so we can substitute that expression into the expression for conc A2 minus, and we get this product. So we can express the concentration of A2 minus as Ka1 times Ka2 times the equilibrium concentration of H2A over H3O plus squared. And so now we have an expression for the total concentration of the molecules, the total amount of the molecules in terms of just the equilibrium concentration of H2A and conc H3O plus, which we can obtain from the pH. We're going to express all of these guys as a fraction of the initial amount. And so concentration initial is going to be the sum of all of those terms that we just outlined, and that'll end up looking like H3O plus H3O times Ka1 plus Ka1 times Ka2. And, well, actually that's not, I just lied. It's a different term, but you add those together, and you get a term for conc H2A initial. And you take the ratios of your equilibrium concentrations of each of the species divided by that initial concentration, and you end up with expressions that look like these. Conc H2A equilibrium over initial goes as H3O plus squared over these terms, Conc HA minus goes as H3O plus to the first power times Ka1 over that common denominator. And Conc A2 minus goes as Ka1 times Ka2 over that common denominator. So something to note about these terms.